and we're very happy that all of you, you're joining, even though it's online. As you know, we're going to have this online workshop for 4 days, today, tomorrow, then next week, Monday and Tuesday as well. So before we start, we're going to have a tour de table where everyone, so you can present yourself, your name, your affiliation, what you're currently doing, and what are your research interests, just to make sure that the examples that we're going to work on are in line with your work. So to make it a bit organized, I will call you. I will just say the first name and then you can present yourself. So we can start with Al-Anud.
Hello, hi. Do you hear me?
Yes, we can.
Hi, this is Al-Anud Al-Ataibi. I am a PhD student in economics at University of Reading. Currently, I am doing my research on women employment. I'm using a labor market survey for Egypt. I'm interested to see what determine women employment in Egypt, especially that there is increasing in education. However, we are not seeing increasing in employment. Yes. Thank you.
Great. Thank you. Asli or Azli? Asli or Azli Dolu?
Yeah, do you hear me?
Yes.
Hello, everyone. My name is Aslı Doluyu, and I am an assistant professor at Bakırköy University in economics department. And my research my research interest in this area of education economics, labor economics, and health economics. Originally from Turkey, and I am dedicated to contributing my files to expertise through religious research and academic inquiry. I also interested in causal inference model because in my PhD thesis I studied the synthetic control method. So thank you for this chance.
Great. Thank you so much. Ashraf Labidi. Ashraf Labidi. Okay. Aya Sirsi.
Hello, this is Ayel Sersi. I'm from Egypt. I work as a lecturer assistant in the Institute of National Planning. I'm also a PhD student in the Faculty of Economics and Political Science. My research interests are economics of environment, natural resources, and specifically green physical policies. Thank you.
Thank you. Ayat Ismail.
Hello, I'm Ayat Ismail. I'm teaching assistant at Faculty of Economic Studies and Political Science, Alexandria University. I'm a PhD candidate in my faculty. I have an interest to write about public policy and institutional economics. Thank you.
Thank you. Evran Kansari.
Hello, everyone. My name is Evren, and I'm a master's student in agricultural economics. Right now, I'm writing my thesis on impact of conflict on non-farm enterprises in Nigeria. So I'm using instrumental methods. And thank you for the workshop.
Great, thank you so much. Fatiha Ageni.
Yes, hello everybody. How are you doing? My name is Fatiha Agni. I'm from Morocco, and my research about income inequalities. And I am in fourth year in University Mohammed V in Morocco. Especially, I'm interested about public policies and applied economics. Thank you for your workshop.
Great, thank you so much. Fatima as the guys.
Do you hear me?
Yes, but would you please raise your voice a bit?
Hello everyone. It's a pleasure to be with you for this very important training. I'm Fatima Azdagas, a doctoral student in economics and public policy at Ibn Tufayl University in Kenitha, Morocco. I'm a part of public policy and economics laboratory. I'm working on the micro-econometric evaluation of social support program for schooling in Morocco.
Great, thank you. Fatiha again, sorry. Hala Bushama or Hala, I don't know.
Yes, hi everyone. Can you hear me?
Yes.
Great. My name is Hala Abu Shama, and I'm from Sudan. I'm a development economist by training, so I hold a master's in development economics from SOAS University of London, and I'm currently a research assistant with IFPRI, so the International Food Policy Research Institute. We do a lot of research on food security, climate change, natural resources, at different macro and micro levels, and also using very different methodologies. Our work, the team I work with mostly focuses on Sudan, and I'm very excited about this workshop. So thank you for having me. Over.
Thank you. Hassan Shari.
Hi, good evening. My name is Hassan Shiri. I'm from Lebanon. I'm an assistant professor of economics at the Lebanese American University. Now, my areas of research from the micro level are the on innovation and upgrading amongst the firm level, so enterprise level data. And on the macroeconomic aspect, I focus on the IMF structural adjustment programs and their impact on MENA economies, notably non-oil economies, as well as the debt determinants or the determinants of sovereign debt distress in the region. So I might be teaching this course the course about applied microeconometrics next term. So that's why I'm taking this workshop. Thank you.
Thank you so much. Maha Balba.
Hello, everyone. Thank you for being part of this workshop. This is Maha Balba. I'm an economic researcher at the Ministry of Communication and Information Technology. I'm pursuing my master degree in development economics in Paris Sorbonne. And my research interest mainly in social protection and social insurance. And this is what I'm doing exactly in my research, in my thesis, and also in my work. And that's it. Thank you.
Okay, thank you. Nadine Omar.
Yeah, hello everyone. My name is Nadine Omar. I'm a PhD candidate and assistant lecturer at the German University in Cairo. My research interests are mainly monetary policy, inflation, and also linking them to both climate change and income inequality. I would like to thank you very much for this opportunity.
Okay, thank you. Muhammad Ali Bougzim.
Hello, everybody. My name is Bougzi Mohamed Ali. I'm from in Morocco. I am a PhD candidate in Qadi University. My research interest in the impact of the regional public policy in regional labor market by computable general multi-regional computable general equilibrium. And thank you for your workshop.
Great, thank you. Rashida Al-Yamani.
Good evening, everyone. Do you hear me?
Yes.
Okay, I'm Rashida Al-Yamani, a professor of economics at Hassan II University from Morocco. My current research studies are interested in the impact of gender on financial inclusion in the MENA region and the effect of corruption on investment growth. For these reasons, this workshop will be benefit for me. Will greatly benefit from the techniques and methodologies that will be discussed at the workshop. Thank you for this opportunity.
Thank you. Rahisi Abdelillah.
Hello everyone, do you hear me?
Yes.
I am Adila Raisi, a first year doctoral student at Mohammed VI in Rabat, Morocco. In recent years, financial inclusion has been a key element in reducing poverty and promoting economic stability and growth. So at this early stage of my academic journey, I'm trying to explore the broad field of financial inclusion in Morocco. Thank you for your attention.
Thank you. Seda Kilisha Aslan.
Hello everyone, my name is Seda. I'm research assistant at Middle East Technical University. My PhD thesis is about financial innovation in firms. Thank you.
Thank you very much. Tahani Mlaye. Tahani. Okay, did I forget anyone before we present ourselves?
That's me.
Sorry. Okay, please go ahead.
I'm Zahra Buru from Lebanon. I hold a doctorate of business administration. I work as an economic researcher as consultative center for studies and documentation. My work center on economic research within the Lebanese context. I train econometrics for undergrad, and that's it. Thank you.
Okay, thank you. Tariq Grahi.
Yes, thank you, and good evening, everyone. My name is Tariq. I'm working as a researcher at Economic and Social Research Bureau in Sudan. My research interest is about education economics and political economy. Thank you.
Thank you.
Sorry.
Yunus Zaim. Yunus. Okay. Did I forget anyone?
Hello.
If yes. Yes, please, Tahani, go ahead.
Sorry, I have a technical issue. My name is Tahani. I'm from Tunisia. I'm an agro-economist engineer specialized in development and management of projects. I work now on a research project, and I need such econometric skills, if we can call it, to go ahead in the analysis of our database as the result of the part one of the project of the research project.
Great, thank you so much. Anyone else? If yes, please go ahead and speak if you didn't present yourself. If not, then we can move to the instructors. Rasha, please go ahead.
Hi, Chahir. Hello, everyone. I am Racha Ramadan. I am professor of economics at Cairo University and ERF fellow. I will be co-teaching this course with my colleague and my friend Chahir Zaki. We used to do this like 4 or 5 years now. I'm so glad to be with you. And hopefully you will find the workshop useful and you can apply it for your research later. Back to you, Chahir.
Thank you, Rasha. I'm Chahir Zaki. I'm a professor of economics at the University of Orléans and on leave from Cairo University. I'm also lead economist at the Economic Research Forum. And as Rasha said, it has been a while that we teaching this course. So we're very happy that we're doing it this year with a diversified set of participants from different backgrounds, different countries, and different specialties. I would like also to thank the ERF team, especially Namis and Passant, for organizing all the logistics behind the workshop, and especially Namis, who will be coordinating all the material and making it available for you. So thank you so much, Namis and Passant. Now, before we start the first lecture, I just want to go through the main objectives of the workshop and how we're going to proceed during the 4 days. And then we start with the first lecture. So I'm going to share my screen, and then if you have any questions, don't hesitate to interrupt me. Can you see my screen now?
Yes. Yeah.
Great. So just a second. Yes. So, as you know, the objective of this workshop is ERF in general has many training workshops addressing either macro issues or micro issues. The first workshop that we're going to have this year is the micro one, which is the applied microeconometrics and public policy evaluation. And the main objective of this workshop is to get acquainted with different microeconometric tools that can be used in policy evaluation and different programs. And this can apply to a whole range of themes ranging from social protection to environment to trade to macroeconomic policies, because at the end of the day, these tools that can be applied on micro or individual data regardless of the theme itself. So day one, which is today, we're going to have 2 lectures with a short break of 15 minutes. So the first lecture is going to end at around around 6:15 Cairo time. And we're going to have a break of 15 minutes. Then we continue with the second lecture until 7. Sorry, because it's a bit disturbing because I'm looking at the watch of Paris time and I'm speaking in Cairo time. So the break is in an hour. And then we're going to have a short, after the short break, we're going to have an hour and a half for the second part of the lecture. So the objective of today will be mainly to talk about the fundamental problem of causal inference, and as you might be familiar with that, the main differences between correlation, causation, how to have a proper identification strategy, and what are the potential solutions that can help us have a proper identification strategy, either based on observables or non-observables, as I will explain later today. So that's the objective of today, which will be a general introduction to the topic and to the main issue that we're going to address through the different methodology that we're going to see in the other on the other 3 days. Day 2, so more specifically, what we're going to see today to discuss the fundamental problem of causal inference, what are different methodological solutions, what are the underlying econometric tools behind, and we're going also to focus on some exercises in Stata, not today because they will be a bit more conceptual, analytical, and theoretical, and then we're going to have Stata sessions starting tomorrow and next week. Day 2 and 3, but we have a slight change because it will be day 2 and 4. So Racha will be presenting 2 methods on day 2 and day 4, and I will be presenting on day 3, and I will come back to that later. So Racha will be focusing on 2 main methods, which are the propensity scores matching method and the difference in difference. So the idea is that after presenting the main problem that which is about causal inference and identification, each day will present a solution. So tomorrow we're going to see the first solution, which is the PSM, the matching methods. And we're going to see also some exercises and applications on Stata using the labor market panel survey that was collected by the Economic Research Forum. And then on the last day of the workshop, we're going to see another solution, which is the difference in difference method, again, with some applications on Stata. On day 3, so which will be next week, I will be talking about the panel data models and what's the theoretical underpinnings behind such models, and then what are different variants of these models ranging from static to dynamic to other types of panel data models that could be applied, and again, to overcome partially at least the problem of identification. So that's the overview of the 4 days. And as I said, while today is a bit more theoretical, analytical, and conceptual, the other 3 days will be a mix of, in general, the first session will be more theoretical, just to understand what are the theoretical tools that we need to understand the econometric method that will be presented, and the second session will be more applied using Stata. So that's why it's very important that you install Stata on your laptop, because it will be much more useful for you if you work simultaneously on the software during the workshop. So we'll also take advantage of the fact that you will be working on Stata in order to develop some Stata skills, in the sense that what are the comments that we can use in microeconometric program evaluation, to have some descriptive statistics, graphing, what are the multivariate estimation commands, what are the post estimation commands that we use in order to test for endogeneity, heteroscedasticity, and all the classical problems of econometrics that we know. What are the commands that we can use in order to reproduce the results and then to document those results? And clearly, all this will help us make sure that the theory that we learn in the first part can be applied in the second part. Before I start the conceptual framework of the identification strategy, I just want to highlight a couple of things that are really important when it comes to the empirical work, and I'm sure that you might be familiar of that, but it's important to frame it before we start the training and before we present the different details of the models. So clearly, whenever we start working with an empirical data set, it's important to start with some descriptive statistics to present the key characteristics of the main variables that we'll be working on. Why is that important? At least for 3 reasons. First, to understand the data itself. What are the trends that we have in the data? What are the basic associations that we have in the data? And this will give already a flavor of what we can get from the empirical exercise. Second, it provides also a background and a motivation for the issue that we're going to study. For instance, if there is an issue of employment, women employment, for instance, or an issue for women in social protection, we have to motivate this through the data itself. And that's why those descriptive statistics will help us motivate the topic that we'll be working on. And finally, also simple graphs and simple graphical representation of the data can give us also an idea about the main assumptions of the microeconometric models, whether the data is normally distributed or not, whether we have a skewness or not, whether we have a kurtosis or not, whether we have a large variability with significant outliers or not. All this can be determined through the descriptive statistics that we can have in the beginning. And that's why, especially at the end, after we run all the proper econometrics that we're going to have, even if it's very important, but it's not sufficient, because at the end of the day, if, for instance, we're doing a program evaluation for the Ministry of Social Protection or for the Ministry of Finance or the Ministry of Trade, at the end of the day, the minister will not read the econometric details because he simply might not be interested in that. What is interesting for the minister is the policy implications and those graphical representations. So that's why it will be very important to work on these descriptive statistics to deliver the main message that we want to deliver from the empirical work. In terms of econometric methods that we're going to cover, in general, this training can take much more than this, but we have this is a condensed version of the training as it's an online training, and we know that online training in general are a bit difficult, and we cannot have sessions more than 3 hours. So that's why we had to have an intensive version of this program, where we're going to focus on 3 main methods, as I said in the beginning. The first one is the propensity score matching tomorrow, the difference next Tuesday, and the panel data models next Monday. If we had more time, we could have covered topics like the regression discontinuity design, RCT, but we're going at least to have a very quick idea of those methods in the general introduction today, even if we'll not really cover the technical details of all the methods. And finally, clearly, after we run the different techniques, it's important to understand the robustness and the quality of the results. So that's why, in general, once we finish the technical part with the econometrics and the first round, I would say, of the baseline results, we move forward with the post-estimation commands, in the sense that we run some commands that will help us run some tests and check the robustness and the quality of the results that we got. We'll also see how to extract those results, because in order to do, an empirical paper, we need to extract the results from data. So we'll see how to save the results, how to extract them, and how those post-estimation commands also will allow us to determine whether the hypothesis, for instance, that we assumed at the beginning are correct or not, which model to choose, which one to not to choose, whether the assumptions, sorry, or whether the hypotheses that we test are rejected or not, and so on. One final thing that will be important also during the workshop is about documentation and reproducibility or reproducibility. And we have to distinguish between a replicable and reproducible study. So in general, and this is especially the case in highly ranked journals, very frequently they ask for the do file and the data that that you used in your empirical analysis. So that's why it's very important to prepare a proper do file that is easily to be understood and easily to be implemented or run, because the easier or the clearer the do file, on the one hand, the author, him or herself will be will be able to work on the data once again. Once, for instance, he or she wants to revise the results after submitting the paper. That's one. Two, if we have several co-authors who are working together, it's important to have the do file as detailed as possible and as clear as possible, because what might be clear for me might not be clear for my co-authors. So that's why it's very important to have a clear and a detailed do file. And finally, as I said, because in some cases the journals can ask for the data and the do file to make sure that the results that are included in the paper are those that have been run in the software. So we call a study that is reproducible if all the numbers presented in the study can be reproduced. In other words, I will rerun exactly what you've done in your own paper with the same data, just to either as an exercise, as a check, as you want. And this is a bit different from the case of replicable study. Because replicable study, if for instance, I did a study on Egypt for the effect of global value chains on women employment using the PSM approach, I can make the do file available, and then Zahra can replicate this for Lebanon, and she is going apply exactly the same method with the same do file with the same commands and see what she gets. So that's why it's very important to document all the findings to reproduce my own results or to make my paper replicable. And the do file, as I said, the easier and the more organized the do file, in later stages, it will be much easier for the author, for the co-authors to work on it again, especially that if we submit a paper to a journal, we can work on it up to 2 or 3 years, for instance. So that's why it's very important to make sure that everything is clear in the do file. So that's that's regarding the descriptive statistics and the reproducible and replicable do files. Before starting also, I just want to highlight what are the different commands that we have in Stata. Because in Stata, as you know, we have different types of files, and in general, Stata is constantly evolving. And if someone creates a new command, it's created through the ado file. And this is significantly different from the do file, because the do file is what you create for your own data set. But the ado file is the file that is, it's the file that is used in order to create a command. For instance, the simple command that we use dozens of times, which is reg, behind this command reg, there is an ado file, which is based on a coding language in order to create this command. And this is the case for every single command in Stata. And in general, you will see that a lot of commands are constantly being implemented in Stata. For instance, for those who are working with high dimension fixed effects models, there is the reg HDFE, there is the PPML HDFE, which is the Poisson pseudo maximum likelihood with high dimension fixed effects, and so on. So that's why it's important to be updated with the recent developments in Stata, because it's really a dynamic field where new commands are constantly developed. So, and in general, whenever a command is developed, it will have its own ado file, and it will have also its HLP file, which is the help file. And as all of you, because I'm sure that you have recently used Stata, whenever you need some examples or to see how to write the command itself, you write help and then the name of the command. So in this case, Stata will call the HLP file, and the HLP file is the file that includes all the examples and instructions to run any command. Okay? So those are basically the three types of files that we have in Stata. Either the do file that you create for your own paper, the ado file that is created for the commands that are developed in Stata, and the HLP file that is used to help researchers whenever they work on a new command. Okay? And clearly, the fourth and final type of files that we have in Stata is the DTA file, which will be your data file. So those are the three types of files that we have in addition to the data file itself, because I didn't add it. I didn't mix it with the other types of files because it's still a bit different, but it's among the things that have to be also, you will need to have it whenever you work on Stata. So those are the main elements before we go into the details of the first session. So I just remind you that it's very important to have a well-organized do file. It's very important to understand your data set, to make sure that you're familiar with the different variables, how they are defined, how they are constructed, what's the unit of measurement, what are the main cross tabulations or correlations that we have before we start all the empirical part that we're going to see during the 4 days. So, any questions before I continue? Any comment?
Excuse me, Shakir.
Yes.
Are we expected to do the readings before every session?
Some of the readings are in the textbook, so we will send you the list of readings at the end of the workshop. But so far, if you want to have some readings to prepare yourself, this is fine. But if not, this is not an issue.
Thank you.
Other comments? Questions? Okay. So if we don't have questions or comments, I will start with sorry. I will start with the first part. So now you can see the screen.
Yes.
Okay.
Yes.
So as I
Yes,
said,
I want to ask that, sorry, do you, after the workshop, do you share the PowerPoint slides
yes,
with
you're
us?
going to have the PowerPoint, the do files, and the data, in addition to the readings.
Thank you.
Okay, so for the next more or less half an hour, we're going to have to see what is the idea behind the major identification problem that we have, and how we can overcome this problem. What are the different solutions that are proposed? So to do that, I will first go through the basic theoretical representation of this identification problem and then present the potential solutions. And we're going also to see at least one example for each potential solution from different published papers in the literature. Clearly, I mean, and you have seen this, I'm sure, at least 100 times during your undergrad and your grad studies on the basic difference between the causation and the correlation. Because when we say that two variables are correlated, this means that there is an association between the two variables. It might be positive, it might be negative, it might be significant, it might not be significant, but this does not mean that one variable causes the other. And that's why, and this is a very frequent error that we do while working on empirical papers, where the correlation is mixed with the causation, in the sense that very frequently we treat correlations and associations as if they are causations, where a variable is going to cause another variable. And this might not be necessarily the case, because, for instance, if we detect a positive association between wages and education. In this case, if I observe this positive association between education and wages because higher education is associated to a higher wage, I cannot say safely that higher wages in general are due to a higher level of education, because it can be the inverse, in the sense that those who have the means to finance their studies, they might be able to have a higher level of education. And that's why in this case we cannot say that, given that there is a correlation between the two variables, we can treat this correlation as a causation. But the inverse is correct. I mean, if there is a causation between the two variables, this definitely means that there is a correlation. And in order to be able to say that there is a causation between the two variables, we have to have a proper identification strategy. And that's what we call the identification problem in econometrics. The identification problem in econometrics starts with the statement where we, given that we have two variables or two series that are correlated, we want to make sure or to identify, that's why we use the word identification, whether one of the series is causing the other. Or in other words, that we have this cause and effect relationship. So that's why most of the empirical tools that we're going to see during this workshop are going to help us answer this question: how to make sure that the correlation that we detect between different variables can be formulated as a correlation between the two variables. Okay? Any questions so far? Okay. So let's formulate this econometrically. And clearly, we're going to need some math to prove this and to understand why, if we do not take this into account in a serious way, we're going to have biased results. So let's assume that we have a treatment. A treatment is a certain policy intervention, like, for instance, an export promotion strategy that will affect that will be from which will benefit some exporters, or a social intervention, like, for instance, a social safety program given to women, given to informal workers, and so on. We call this a treatment. And if we have a treatment, we have to distinguish between two groups, what we call the treated group and what we call the control group. So the treated group is the group that is going to benefit from this intervention. in the sense that it applies to exporters who are going to benefit from the export promotion program, or it applies to women who are going to benefit from the social safety net, and so on. And the control group is the group that will not benefit from this policy intervention. So if we regress Y, which is the outcome variable, so let's say that we're going to examine the effect of the social safety net program on women empowerment. In this case, the outcome variable is going to be women empowerment, and the treatment is the social safety net program. So we're going to regress Y on X, where Y is the outcome variable or the dependent variable, and X is the policy intervention or the main independent variable with the error term. So in this case, if X is the treatment, this means that beta 1 that you can see here, beta 1 that we have here is going to measure the difference between whether X is equal to 1 and it shows that there is a treatment, or X is equal to 0 and there is no treatment, which is the case of the control group, because as I said, we have the treatment and the control group, and the treatment or the treated group, sorry, is the group that will benefit from the treatment, which means that in this case, X is going to be 1. So 1 multiplied by beta 1 is equal to beta 1, which means that at the end of the day, this beta 1 is going to determine the effect of the treatment. But if the individual does not benefit from the treatment, in this case, X is going to be 0, and 0 multiplied by beta 1 is going to be 0, which means at the end of the day that beta 1 is going to measure the difference between those who benefit from the treatment and those who did not benefit from the treatment. And this is what we have here in these two equations, where y1 dot is equal to beta 0 plus beta 1 plus the error, compared to y0 that includes the individual that did not benefit from the treatment. That's why, because as I said in the beginning, if I do not benefit from the treatment, X is going to be 0, and beta multiplied by X is going to be 0, and that's why the whole term will vanish from this relationship. So in this case, if I take the difference between both, between y1 and y0, so the beta 0 will cancel out, and I will have the first error term minus the second error term. That's what we have here. And beta 1 is going to measure the difference between those who benefited from the treatment compared to those who did not benefit from the treatment. So at the end of the day, the OLS estimate in this case, which is beta 1, will measure the difference between those who benefited from the policy intervention compared to those who did not benefit from the policy intervention. And that's why, in theory, beta 1 should be fine, in the sense that beta 1 is going to measure the difference between the two groups. And at the end of the day, what I'm interested in as a policymaker is to see whether my policy intervention is effective or not. But we're going to see that econometrically, this beta 1 can suffer from different problems. And that's why, just a second. So that's why in this case, if we assume that the treatment is randomly assigned, then in this case, X is uncorrelated with epsilon. And that's here, I remind you that we had in this relationship X and epsilon. And we know from the OLS assumptions, one of the most critical and most delicate assumptions that we have in the ordinary least squares estimation approach, an assumption which is the orthogonality assumption. Do you have any idea about the rationale behind the orthogonality assumption? If you do, please go ahead and speak. So my question is, what is the rationale behind the orthogonality assumption? Any insights? Any volunteers? So the basic idea of what does orthogonal mean in general, not in econometric terms? Orthogonal means that we have two variables that diverge from each other, or that two perpendicular lines. We call them orthogonal. And the orthogonality assumption in econometrics means that the correlation between the explanatory variable and the error term is equal to 0. In other words, the covariance between x and the error term is equal to 0. Why is that important? I will ask another question before answering why is that important. What does the error term represent in econometrics? What do you think? What does the error term represent?
I think if the error term includes all the explanatory variables that we didn't account for in our OLS equation.
Great. So as Aya said,
Also, it represents shocks.
Or the shocks potentially, but in general, it includes all the factors or the variables that are not included in the equation itself. So if, for instance, I'm examining the effect of the policy intervention on women, so if, let's say, the education background of women affects the policy intervention, if the education level is not introduced in the model, then it will be in the error term. So at the end, the error term is going to include all the other factors that are not explicitly introduced in the model. And how we call this in econometric term, if there is a variable, an important variable that should be in the model, but we didn't include it in the model. Do you have any idea about how we can, or what is the name of this problem in econometrics?
Endogenous variable.
Sorry?
Endogenous variable.
Endogenous variable, I mean, endogeneity can be due to that. But if there is a variable that is important and that is not included in...
It's a specification bias?
Specification.
Yes.
Specification bias or...
Omitted variable bias.
Sorry?
It's an omitted variable bias, right?
Exactly. It's the omitted variable bias. So the omitted variable bias means that there is a variable. There is an important variable that should be included in the model, but we didn't include it, and that's why at the end of the day, there is an omitted variable bias, which is associated to a misspecification in the sense that the model is not correctly specified. And if the model is not correctly specified, this will lead to an endogenite. Okay? So back to the initial question, the orthogonality means that the correlation between the explanatory variables and the error term is equal to 0. And why do we have this assumption? Because if the error term is correlated to the explanatory variable, this means that the changes in the explanatory variable can affect potentially the changes in the error term, which means in this case that the effect of the explanatory variable on the dependent variable will not be solely due to the explanatory variable, but it will be due also to the change in the error term. And that's why at the end of the day, if if x is correlated to the error term, epsilon, So in this case, beta, the change. So the change in x, or let's put it this way, the change in the error term will lead to a change in x, which will lead to a change in y. So at the end of the day, beta 1 does not only reflect the effect of x, but it will reflect also other things. And that's why if we have this assumption of orthogonality not satisfied or not verified, this will lead to an omitted variable bias, and the omitted variable bias will lead to inaccurate or biased estimators. Biased estimators, in this case beta 1, means that we do not really measure accurately or precisely the effect of x on y. So, any questions on this before I proceed? Any questions? Anything that's not clear?
All clear.
Okay, so in this, sorry, just a second. So in this case, if we assume that the x, which is the treatment, is randomly assigned, then x is not correlated with the error term. And if x is not correlated with the error term, this means that the x is exogenous. And if it's exogenous, this means that the estimated parameter of beta will not be biased. Why is that the case? Because if the x is randomly assigned, this means that in this case, the error terms will be equal. And if the error terms will be equal, then this term will vanish, this one, because they will be equal. And if they are equal, this means that the difference between y1, those who have been treated, compared to those who have not been treated, is equal to beta 1. So beta 1 really, in this case, reflects the difference between y1 and y0, as long as x is randomly assigned and that there is no correlation between x and the error term. Hassan, yes?
Yes, excuse me, Shahir. So when we enforce this assumption of the orthogonality assumption, this means automatically the epsilon 1 minus epsilon 0 is removed, right? This becomes 0.
Exactly. But I mean, as long as this assumption is verified, so that's why we have
Of
to
course.
test whether this assumption is verified or not. But as long as it's verified, we can say that. Other questions?
Does this assumption hold in real life, yani, in real example, that
I mean,
epsilon 1, or it will be the smallest one?
No, in general, I mean, let's say in 90% of the cases, it will not be verified. And that's why in 90% of the cases, we're going to have an endogeneity. And the endogeneity means that the orthogonality assumption is violated. And if it's violated, then we have to resolve this problem to get consistent and unbiased estimators. And that's what we see here. If this assumption is verified, so you can see here that the keyword is that the treatment is randomly assigned. And as a consequence of that, x is not correlated with the error term. And if x is not correlated with the error term, that this reflects the fact that the two error terms will be the same. And if they are the same, in this case, the difference between the two outcome variables will be only the beta 1. So in this case, we can say that the OLS estimate of beta 1 gives the average treatment effect or the policy intervention that we had. And in this case, the difference between the treatment and the control is the unbiased estimate of beta 1. So beta 1 really reflects the difference between the treated and the untreated group, as long as, again, I'm saying that in this case, the OLS estimate of beta 1 will be unbiased as long as X is uncorrelated with the error term, which can vary, I mean, rarely can happen. Why is that the case? Because in most of the cases, the two errors will not be equal. And why is that? Because we might not have this randomization, in the sense that nothing guarantees that X is uncorrelated with epsilon. And if X is correlated with epsilon, this means that the orthogonality assumption is not verified. And if the orthogonality assumption is not verified, then any change in X will affect the change in the error term. And the change in X and in the error term is going to affect Y. So that's why beta 1 will not reflect only the effect of X, and that's why it becomes biased. So let's prove this through some math to make things clearer. We're going to have the same initial relationship that we have seen, where y1 minus y0 is equal, as you can see here, beta 1 plus the difference in the error term of the treated and the control group. Okay? So if X is correlated with the error term, this means that the two error terms are not equal to each other. And in this case, the difference between y1 and y0 will not reflect only, will not lead to the estimation of beta 1 that reflects the difference between the two y's, the outcome and the outcome of the treated and the outcome of untreated. But it will also reflect another quantity that depends on the correlation between X and epsilon, which is this part. So how to mathematically prove this in the case where there is no randomization, in the sense that X is not randomly assigned, and if X is not randomly assigned, then in this case, the error terms will not be equal to each other. So I will just remind you with the basic elements that we have seen in the OLS derivation. So if we regress y on x, the OLS estimation, we're going to have y that is equal to beta 0 plus beta 1 x plus the error term, where y is the dependent variable, beta 0 is the intercept, beta 1 is the slope, and x the explanatory variable, and epsilon is the error term. And we know that beta 1, which is the coefficient estimated by the OLS, is the ratio between the covariance between x and y relative to the variance of x, or the covariance between x and x. And again, here, the OLS estimation of beta will be the ratio between the covariance between the explanatory and the dependent variable relative to the variance of the explanatory variable. And the variance of the explanatory variable or the covariance between x and x. So we can rewrite that. So we're going to replace the covariance between x and y by the covariance of, so y here is all this part. So that's the first part. And x, it remains as it is, right? And then in the denominator, we still have the covariance of x and x. Clearly, what is the covariance? The covariance It shows how the two variables change together, or I mean whether they change in the same direction or in different directions. So based on this, if we in the numerator here we have the covariance of the first term and the second term, right? So we can split this into two parts because at the end of the day, beta 0 is an intercept, so it does not affect mathematically here the numerator. So we can say that the covariance, as if we're multiplying or we're factorizing x with the first term and the second term. So it will be the covariance of x, and we take out beta 1 here, plus the covariance between the epsilon and x. So again, what we did here in this step is that here this beta 0 is constant, it's the intercept. And then we're going to calculate the covariance between this term and this one, and this term and this one. So we have this covariance and this covariance, okay? If we get rid of the denominator with the same numerator, because here we have the denominator and the denominator that are the same, so they will be simplified together, and we get from this part only beta 1, because the covariance of x and x will be simplified with covariance x and x. So we get here the beta 1 plus the ratio of the covariance of epsilon and x that we got from this part relative to the covariance between x and x. Okay? So the estimated parameter of the beta if we use OLS will be equal to beta 1 plus a second quantity that we have here, right? The problem is that if the assumption that we assumed, which is that the covariance between the error term and the explanatory variable is not equal to 0, this means that this ratio is not equal to 0. And if it's not equal to 0, this means that the parameter we estimate will not be equal to the true parameter of the population, but it will be equal to the true parameter of the population plus this second term, right? And that's why in the beginning, when we assumed that x is randomly assigned, the covariance between the error term and x is equal to 0. And that's why this ratio will be equal to 0. And in this case, beta OLS will be equal to the true parameter beta 1, which means that it's not biased. But if this ratio is not equal to 0, this ratio is not equal to 0, this means that the parameter that we are going to estimate is not solely equal to the true parameter of the population, but it's equal to the true parameter of the population plus another parameter that will depend on the covariance between epsilon and x. So the whole problem that we currently have is whether the covariance between the error term and the explanatory variable is equal to 0 or not. Any questions on this first part?
Yes, please, Chahir. So what's the rationale behind the following, that randomization guarantees the assumption?
Because this means that the treated group is random. It's not pre-selected or predefined, or there is no some common characteristics between among the treated group that make those individuals, for instance, self-select themselves. Because, for instance, if I'm examining the effect of the social safety net program on women empowerment, perhaps women that are going to benefit from this program are on average more educated, and that's why they will take the initiative to go and register themselves. which means in this case that the treated group is not really random because it includes mainly more educated women. And that's why we cannot really say that the treatment was random.
Okay, so we take it as given that in randomization, the orthogonality assumption is guaranteed.
Yes.
Okay,
If it's not the case, then in this case,
we probably need another model or something.
Sorry?
Then we probably need another model if it's not guaranteed.
No, I didn't hear the first part.
Sorry, I mean, even if we have a random sample, it might be the case that in this random sample, we have X and epsilon being correlated, and therefore the orthogonality assumption may not hold. I'm just raising this concern.
Well, I mean, here we're talking really about not a random sample. I'm talking about the treatment itself is random.
Okay.
And we don't have a self-selection, for instance.
Okay. Thank you.
Another example to clarify this, because I've been talking about gender and women empowerment, I will talk about a trade example. That part of the literature argues that exporting firms are on average more productive, which means that if I restrain my sample to exporting firms, on average, they will be more productive. And perhaps if they are more productive, they are more likely to benefit from any government support. So that's why I have to make sure that the treatment I have is not, that the treatment that I have is random. Okay, in this case, the export, for instance, export promotion program is random and not limited to a sample of self-selected exporting firms that decided because they are either managed by more educated managers or they are more productive, and that's why they benefit from the program. Okay, any questions? Okay, so in this case, just a quick refresher on the assumptions of the linear regression model. I remind you that one of the assumptions was that we have strictly exogenous regressors. And that's why it's important here to distinguish between strictly exogenous and weakly exogenous. So when we wish to analyze the effect of all of the explanatory variables, any question? Maha, do you have a question? Okay. So if we wish to analyze the effect of all the explanatory variables on the responses, we're going to have different assumptions. So the first assumption is that the expected value of y conditional on x will be equal to the parameters and the explanatory variables, because here, as if we're looking at the average, the expected value of y conditional on x, x's are stochastic. We have a constant variance, homoscedasticity of the error term, and then the variance of y conditional on x is also equal to sigma square. Y conditional and x are independent random variables, and y is normally distributed. So as long as all those assumptions are verified, still I didn't talk about the orthogonality assumption because this is the next one. But if all these assumptions are verified, this means that the parameter that we get an unbiased estimator of beta. Unbiased estimator, it means that the expected value of beta is equal to the true parameter of the population, and that the Gauss-Markov property of OLS are verified, which means that it's the best linear unbiased estimators. And then if this fifth assumption holds, in this case, we can use, if we have a normal distribution, we can use the test statistic and F statistic to run the different inference inferential tests to test for the significance of the variables of the model, etc. Okay. And finally, the last important assumption is that the expected value of the error term conditional on x is equal to 0. And this emanates normally from this assumption, because if the expected value of y conditional on x is equal to the parameter and the explanatory variable, this means that the expected value of the error term conditional on x is equal to 0. Okay? Yes, Tahani?
Just I have can you
Tahani, can you please speak louder, because I can't hear you very well?
okay, I demand a favor. Can you, sir, give us examples or domain of or example of application of each for each methods or of each characteristic that you talk about?
No, would you please say it again, please?
I ask you to give us applications or applications means examples or in any case we can applicate this method and in which other case we should applicate another methods or another characteristic in the same methods.
Well, I mean, we can here. I'm not really talking about specific cases, because I'm just talking about the theoretical idea behind behind the orthogonality and the identification problem. For the examples or the concrete applications, we're going to see this once we start the specific estimation methods. But so far, what's important is to bear in mind first the importance of the identification problem, and how if we do not properly identify the relationship between the variables, we cannot determine the cause and effect relationship. That's one. Two, what are the implications of the non-verification of the orthogonality assumption, which implies that the covariance between the error term and the explanatory variable is equal to 0, because if it's not 0, this means that we are not able to accurately estimate the parameter.
Great.
And finally, to what extent the other assumptions, when they are verified, in the sense that the normal distribution assumption that is verified, etc., this helps us have all the inference statistics that we can do.
Great, thank you.
Any other questions?
It's okay now.
Okay.
Thank you.
So just to summarize once again the orthogonality assumption, and why did I say in the beginning that it's a very delicate assumption? Because in general, I mean, among the, let's say, the 8 or 10 assumptions of OLS, let's say around 7 assumptions, they can affect the efficiency of the parameter. The efficiency of the parameter, it means that the parameter can still, the estimated parameter can still be unbiased, but it's not efficient. And efficient mean that it might not have the lowest variance, but still it's not biased, which is fine, because between unbiasedness and inefficiency, unbiasedness comes first, because we cannot rely on a biased estimate, right? And in general, when we say a blue parameter, the best linear unbiased estimator, the best it's among the unbiased estimators. So that's why if most of the OLS assumptions are not verified, we can still estimate beta 1 or the slope consistently, and we can make inference with some minor adjustments. But if the assumption of orthogonality is not verified, which means that the error term is correlated with the explanatory variable, this means that there is a misspecification bias and that the expected value of the error term is not equal to 0, and therefore we have a biased estimator. And that's why this is one of the most serious assumptions that will really affect the results of the estimation. So as I said, endogeneity in this case does not allow to estimate beta 1 consistently. And if there is a strong endogeneity bias, our estimated model can be a poor description of reality. And why it can be a poor description of reality? Because as I said in the beginning here, the parameter I'm estimating, which is beta OLS, is not equal to beta 1. Beta 1 is the reality, and beta OLS is an estimation of the reality. If the covariance between the error term and the explanatory variable is not equal to 0, then what I'm estimating will reflect the reality and another quantity. That's why it does not reflect only the reality. And that's why if we have an endogeneity problem, what I'm estimating does not reflect what's going on in the real world. Tahani, this is an old hand, or you have a question? I think it's an old one. Okay. So that's the orthogonality assumption. And in general, when we have this orthogonality assumption, we have to talk about strong and weak exogeneity. Because if we talk about the concept of exogeneity first, the first item that has to be verified is that the error term is independent from X, okay? Or, in other words, conditional mean independence in the sense that the expected value of the error term conditional on X is equal to 0. And in both cases, this means that we have an exogeneity. What's the idea of exogeneity in this case? It means that all the other factors that are not accounted for or that are not explicitly introduced in the model, they will not interfere with what we're going to estimate. Because if they interfere, this means that we will not be able to get an accurate estimate of beta 1 on the parameter. Sorry, the effect of X or the treatment on the outcome variable, which is beta 1. It will not reflect, as I said, the reality. Okay? So the last two things before we break, we have to distinguish between weak and strong exogeneity. What's the idea of weak exogeneity? In general, weak exogeneity means that we call a variable that is weakly exogenous, that in general, when we condition on these weakly endogenous variable, we do not lose any information about the parameters of interest. How to explain this? Let's take the example that we have random variables, x1 until xt and y1 until yt, and we have a joint probability density or mass function for these variables that is denoted by f y1 until yt and x1 until xt. So if we repeat this conditioning for this joint probability density function, it will be the product of t from 1 to capital T of x and y, so x and yt, conditional on all the other variables. Okay? And we can do this also for, as you can see in the second line, for the product from t equal 1 until t of f that of y conditional on y1 until yt minus 1. So all the previous values and x1 and other xt's, and the same for xt from y1 until yt minus 1 and x1 until xt minus 1. Here I'm talking about weak exogeneity. Why? Because I'm conditioning on all the other variables without including any information about the parameter of interest. But so far, we didn't talk about the parameter of interest. So that's why if we have this joint distribution that is characterized by a vector of parameters of interest, which we'll call theta and phi, for instance. So we're going to have in the first relationship that we had here, the theta, and here the phi. And that's what is written here. So the joint distribution function that we have here, we have the theta and the phi. So in this case, we can ignore the second term that we have here for inference about theta, as long as the x variables are fixed. So if this assumption holds, the fact that x is fixed, then in this case, we can say that the explanatory variables are weakly exogenous. But if we talk about a weak exogeneity, this means that there is a strong exogeneity. And for the strong exogeneity, it's a bit similar to what you have perhaps seen in the Granger causality idea, which is in this case x conditional on y until y minus 1 and x until xt minus 1 and phi. In this case, which it will be equal to x conditional on from x1 to xt minus 1. So in this case, y does not Granger cause x, in the sense that y does not affect x. It's only x that affects y. If I'm certain about this direction of causality, then in this case, we're talking about strong exogeneity. So in other words, conditional on x1 until xt minus 1, the distribution of x here does not depend on the past values of y, while it was the case here. Here, if you remember, x was conditioned on the previous values of y. Here, it's not the case. And if it's not the case, then in this case, y does not Granger cause x. And if y does not Granger cause x, in addition to the weak exogeneity that we have seen, we can talk about a strong exogeneity. Okay? So basically, the main difference between weak and strong exogeneity pertains to 2 points. First, whether there is a loss of information about the parameters of interest when we condition on one of them or not. And second, whether the x's depend on the historical values of or the past values of y or not. And that's why when we have this weak or strong exogeneity, we can get the efficient estimators that we've been talking about. Okay, so in this case, this will help us identify the causal effect. In other words, to determine whether the association between some variables is really a cause and effect relationship. And in this case, we will see the different methods, either using experiments or quasi-experiments or observational data in order to determine this cause and effect relationship. Okay? I will stop here because it's already 5:30. Any questions? So if we don't have any questions, we're going to break for 15 minutes and we'll be back at 6:45 Cairo time, so in 15 minutes. And then we're going to have an hour and 15 minutes for the second part.
Mr. Shahir,
Yes?
the question is about the recent rise.
Yes.
A link.
After the break. After the break.
Do you know what I mean? Did you get it?
Yes, but I mean, we're going to address the question after the break because we're running now out
Great.
of time.
Great.
Okay. Any other questions or comments? Sorry. So we will meet in 15 minutes and we start with the questions and with the last part that I did not cover. Thank you and see you in 15 minutes. Okay. Before the questions, I just want to finalize the last part because we haven't finished it yet. Just a second, I'm sharing the screen. Okay. Two final things very quickly. So as I said, in all of these models, it's important, or in other words, all these models, they help us determine the causal effect that we're interested in. And in general, we can use either experimental approaches or some observational data in order to determine this cause and effect relationship. In addition to all that, I just want to introduce a concept that perhaps some of you either have seen or have already used, which is the structural models concept. Because a structural model in general, uh, it's a model that represents a causal relationship in the sense that in most of our empirical research in general, we have some statistical associations that capture some relationships. But in structural models, by structure, which means that the structure of the model itself leads to the existence of a cause and effect relationship. And that's why, in general, a sampling-based model in general is derived from from the knowledge of the mechanisms used to gather the data. In other words, in this case, we are we will be able to identify the different mechanisms that we have, in the sense that we will be able to distinguish between the cause and the effect thanks to the structure of the model. Okay, and again, those structural models, they help us have this causal relationship. And this is different from what we do in general, which is the reduced form estimation, because in the reduced form estimation, I just estimate the relation between different variables, and I might have to test for the existence of an endogeneity or not. So we will not tackle in this workshop structural models, but I just want to highlight the idea behind, just to have it in mind. So that was the first part of today's lecture. I just want to recap with the main concepts that we have seen. So we started with the first idea, the treatment and the control, and how we want to compare between the treatment and the control to examine the effect of the policy intervention. That was the first point. The second point, to what extent OLS estimations can be unbiased if the correlation between the explanatory variable and the error term is equal to 0. And this holds as long as the treatment is randomized. If it's not the case, this means that the correlation is not equal to 0 between the explanatory variable and the error term, which means that the error terms are not equal, and therefore what we're estimating is not really the effect of the variable or the policy intervention on the outcome variable. And that's why it's biased. And that's why, the last and final point, we have to resolve this through different techniques that we're going to see. Any questions? So I remember that Hani had a question before we start the second part. Tahani?
Okay, thank you. Actually, my question is about the download of this data software.
Sorry, about what?
The download of this data software. I tried to download two versions using DVD, but it failed. I can't install the software on my PC. What should I do?
You cannot, you mean you cannot install the software on your laptop?
Yeah.
Okay. Which version of Stata do you have?
15.
15. Well, in general, I don't know what I don't know what kind of problem you have, but
is demand this authorization code?
yes, that's normal, because Stata is not a free software. So you have to either you have to search for an old version that might be free. That's the first option. Or you ask at your university about the license.
Great. Old version, we can. The problem that I don't have time to go and search. So
I mean, you can, for today we're not using Stata. Tomorrow you will be using Stata. So try to search online for a free version that you can use tomorrow, even if it's old, because I think that tomorrow the commands will be rather basic. And then you will have the rest of the week to check at the university, because in general, in most of the research labs at the universities, they have a student license or a researcher license that can and that they can give it to you.
Great. You just give me some solution. Thank you.
Okay, thank you. Other questions?
No, for me.
Okay. So,
Good evening.
good evening.
Sorry for any interruption. I just wanted to say that I have a Drive link, so I can share it with, I don't know how to pronounce her name, but I think Tahini.
Thank you.
Yes, I can share it
Well,
with you.
okay,
It's a
I
free
mean,
version.
given that it's not, I mean, I will let you discuss this bilaterally because it's not an official version in ERF. So I will let you discuss this bilaterally, okay?
Okay, but this is an official version, I mean.
I'm not sure because in general, I mean, you can check, but I will let in all cases it's not for ERF to find a license. So you can discuss this either bilaterally or by email or what you prefer.
Okay, thank you.
Okay. I will now share the second part. So in the first part, I presented the problem. Now we will have to see what are the potential solutions with some concrete examples. So we're going to have around an hour to discuss this. Hopefully we'll be able to finish that. Just a second, I will just put the charger. Okay, so if you remember, we said that in general, the fundamental problem that we face in such estimations pertains to the fact that we want to distinguish between the cause and the effect. And we want really to determine what is the effect of a specific intervention on a specific outcome. And the problem is that in some cases, it's very difficult to identify what we call the counterfactual. Let me give you an example. If we have, for instance, a policy intervention from the government where they would, where, for instance, during COVID, some governments, I mean, in different countries, they supported informal workers. And we want to determine the effect of this policy intervention on informal workers, whether it was beneficial or not, and so on. Okay? If we announce that there is a program, and then informal workers are going to apply and they are going to benefit from that. The problem is that if I want to compare whether the program was beneficial or not, I have to compare logically. I can compare before and after. How was the informal worker before getting this social safety net, and how was the informal worker after getting the social safety net? Which means that I'm comparing before and after, as I said. But the problem of that is that it's not really accurate, because what I should have been comparing is what is the status of the informal worker after getting the social safety net program, and what would have been his status if he didn't get the social safety net. But the problem is that the second point I'm talking about, which is what would have been his status if he didn't get the government support, it's not observable. Because what I observe, either the individuals who got the support, let me show you this on a graph. So I have here T0 and T1, okay? I have here before the intervention, and this one is after the intervention, okay? And I have two types of individuals. Whether those who benefited, yes or no, okay? So before, no one benefited, right? Because here it will be 0 and here it will be 0, because no one got the government support program. After the intervention, those who benefited here and those who did not benefit are here. What I want, if I want to determine the effect of the intervention, it's not really accurate to compare before and after. Why? Because ideally, what I wanted to calculate is the difference between those who got the support in T1, this one, compared to the same individuals in T1, but if they did not get the support. But the problem is that in the real world, I cannot observe this. What I can observe in T1, either those who benefited or those who did not benefit. But I cannot observe what would have been the status of those who benefited if they did not benefit. And that's why, if I'm not able to identify this group, I have to find a counterfactual or a control group. So the control group that I will be comparing with, okay? But we have to bear in mind this idea because in general, it's very important to make sure with respect to what we are comparing, okay? So back to our discussion on in the real world and the participation in those programs. And as I said, it's always very difficult the impact to identify the impact of public policies, given that I'm not really and this was raised in one of the points that we discussed that I discussed with Hassan on what are the determinants of participating in a program. Because, for instance, participation in a program can be affected by other factors that explain why some individuals participate and others do not participate. So, as I said in the beginning, indigeneity in this case means that the assignment to treatment is not random. And it does not only depend on observables, but it might depend on unobservables, on some things that we do not observe in the individuals, right? And at the same time, the outcome itself can be affected by some observables that some characteristics that I can observe, or some unobservables. For instance, in 2015, Egypt developed a program called Takaful and Karama. Takaful is solidarity and Karama is dignity. And it was a program to support women and elderly people. And as I said in the beginning, if I want to examine the efficiency of Takaful and Karama, in this case, I want to compare the effect of the program for those who benefited from the program compared to their status if they did not benefit from the program, but I cannot observe that. And in addition to this, perhaps for this program of Takaful and Karama, it's very difficult to compare, or not possible to compare the beneficiaries of Takaful and Karama to non-beneficiaries of Takaful and Karama, because in general, those who benefit from Takaful and Karama are poorer. And if they are poorer, any marginal change will show that the program can have an impact, right? So that's why it's a bit difficult to compare beneficiaries to non-beneficiaries in this case. And that's why in this case, it's important to determine what would be the alternative control group if I cannot observe this ideal control group that I'm searching for. That's why in this case, the solutions would be either to have a random assignment, that's the first option, or to use some quasi-experimental solutions. And the quasi-experimental solutions, we have two types that we're going to see, but not all of them because we don't have time. So the random assignment will go, and I'm going to will help me overcome the problem that I was talking about, because we said that one of the main issues that we have is that the assignment itself is not random. If I manage to make the assignment random, in this case, I will not have a correlation between the error term and the explanatory variable. The orthogonality assumption will be verified, and I will not have biased estimators. But if I'm not able to have the random assignment, and we will discuss later why, we can use some quasi-experimental solutions. And for the quasi-experimental solution, they are either based on there is a conditional exogeneity of placement or an instrument of placement. In other words, I will try to see what determines the placement itself, okay? And for the instruments of the placement, this what we'll not see, and this includes the regression, discontinuity design, and IV, or the conditional exogeneity of placement based on observables, and I'm going to explain that. And this includes the three methods that we're going to see, which is the difference in difference, panel data, and the propensity scores matching. Okay, Hassan?
Thanks, Shahid. Just to make sure I understood correctly, so the counterfactual in this case would be the following. The treatment group would have been randomly selected. That's the counterfactual. We're assuming that since if we want to have a random selection of the treatment group, this is the counterfactual. Mahek, this is how the quasi-experimental solutions work. This is how we solve.
You're mixing two things.
Okay.
For the random assignment, in this case, I will not need the quasi-experimental solution, and I will explain this in a few seconds.
Okay.
But when I talk about the quasi-experimental solution, I will try to find the most appropriate control group that will be compared with the treated group. Why? Because in the real world, I'm not able to identify what would have been the status of the individuals that benefited if they did not benefit, because simply what I observe now is the individuals that benefited.
So for now, we just want to see the random assignment, right?
We will start with the random assignment and then go to the quasi-experiment.
Okay, thank you.
So for the random experiments, it's basically based on the RCTs, what we call the randomized control trials. And you heard about them definitely, because all of you, you know that I think in 2019, it was Esther Duflo and Banerjee who got the Nobel Prize for their work on RCTs. And in this case, RCTs, the randomized control trials, we have a random assignment. And if we have a random assignment, this means that we resolved the first problem that was the reason behind of all that. And in this case, we're going to have a random allocation of the intervention, which means that all the individuals in the beginning, they have an equal chance of being selected into the program, right? Or receiving the treatment. And if all of them ex ante, which means before the program itself, they could be potentially beneficiaries to benefit from this program, then I will be able to identify two groups, the treatment group and the control group. And they are directly comparable. Why? Because since the beginning, all of the individuals, they were eligible or they had the chance to be part of the program. Okay? And in this case, there is no selection bias because I did not pre-select the individuals, for instance. Okay? But everyone could potentially have made it. And this is why by eliminating the selection bias, randomization will allow me to compare between the treated group and the control group, or between the participants and the non-participants. And in this case, I will be able to accurately determine the impact of the program, right? Because at the end of the day, I can observe the status of those who benefited and those who did not benefit in the beginning, and it's randomly assigned, it's not pre-selected. And ex post, the difference between those who were selected and those who were not selected will be primarily attributed to the program that was implemented. So the most important point here is that the treatment itself is random. And as long as it's random and there is no selection bias, then we can compare between the two groups. The problem of those experiments is that there are a lot of ethical and political obstacles. Why? Because we have to go to the villages, for instance. We might, in several countries, the researchers, they have to get a lot of permits and a lot of security clearance in order to do those experimental designs. And it's time and resources and money consuming. The cost is very high. The monetary cost is very high. In some cases, it can become a bit difficult to randomize individuals at all. I mean, at the level, it's difficult to randomize at the level of individuals, or to guarantee that the design itself is sufficiently random. And then the problem also can be due to the fact that those who accept to participate, they can, at a certain point, they can accept to participate, but partially, or they can participate, but they can stop the program, or also some individuals of the control group who did not benefit from the program, they can search for other alternatives. Example, if we run an RCT, a randomized control trial in a village to support exporters, and we're going to see this example. So exporters of carpets who do not benefit from this program, they know that they do not support, that they know that they will not benefit from this program. And if they know this, they might search for other solutions or other potential donors to support them, right? Which means that in this case, the control group that must include individuals who do not benefit from any program will be contaminated. And contaminated means that it's not a purely control group, in other words. Okay? So that's why even with RCTs, we can have a lot of problems. I will present two cases from two different fields, one from labor and the other from trade, one from the Dominican Republic and the other from Egypt. So the first one is the paper by Card et al. Of 2007, where they were examining the impact of training on labor market for the Dominican Republic using an RCT. So what they did, what the government did this time is that from 2001 to 2005, the government of the Dominican Republic implemented a training program called Fomento e Empleo, and the basic idea was to support youth in order to get employed later. And I targeted a specific category of the population, which is whose age is between 18 and 29, and their education level is less than secondary education and in urban areas. The training included several sessions and several weeks where basic and vocational skills have been basic and vocational skills session have been delivered by private trainers, and they had also after the training to benefit from an internship. This paper evaluated the impact of this training on youth in order to see whether individuals who benefited from this training and which means those skills session and the internship, they were more able to find a job or not. So they did this with an RCT, in the sense that they identified first all the individuals that have equal chance to participate to this program, and then they proceeded as follows. Each time they had 30 eligible applicant, and over the 30 eligible applicant, 20 were assigned to the treatment and 10 to the control. Which means that in the beginning, and here there is a very important word, which is eligible, because in the beginning, the 30 are eligible. And over the 30, some of them will benefit from the program and others will not. Okay? And then they had another important point where up to 5 individuals from the control, because I remind that we had 10 in the control. So up to 5 from the control could be reassigned to treatment if those who have been assigned to the treatment, they failed to show up or to participate in the program, or they decided to leave the program, dropouts. Okay? And then the train took place in 2004 through a registration form to determine who can participate and who cannot participate. There was a follow-up survey in 2005 in order to determine the outcome, okay, and how they evolved over this duration. The sample included more than 8,000 eligible applicants, more than 5,000 that, or almost 6,000, they were assigned to the treatment, and around 2,500 they were controls. Okay? And the follow-up data was done with some individuals, but clearly there was some dropouts, and this might bias the results, but I mean, you can't do anything at a certain point, so you have to do with what you have. And then they examined the effect of this training on different labor market outcomes. First, the employment. Second, the hours to work, the hours of work, the wage. And they wanted also to measure the quality of jobs through whether or not the individuals have a health insurance in their job or not. Okay, I mean whether they can get a job with a health insurance or not. So those were the four labor market outcomes that were examined. So to summarize the impact, and you will also see that the paper will be made available with the readings, but in general, uh, the uh, the as you can see here, the results show that there is no impact on employment, hours of work, some differences in the monthly earnings, and no significant difference in health insurance. That's the global impact of the intervention, which means that the impact of the intervention was rather limited. And this per se is a finding, because if the government is going to spend huge amounts on a certain program, and if they want to have an evidence that that this program worked or did not work, they need this kind of studies. Okay. And the main lessons that are learned from Card et al. Paper is that the randomization in general is, I mean, it's the first best, but in general, the reality of randomization is difficult, or it's not simple to apply because of the different problems that we talked about: the contamination of the control, the reassignments of the control, the imperfect compliance, then some selection bias in the sense that perhaps those who do not drop out, they are on average better than their counterparts. And at the end of the day, the main finding was that the program, if the effect of the program was limited. Okay. The second case study was a bit different, even if it uses the same method. And just for your info, in general, among those who run such impact evaluations, are primarily working for GPAL, which is the Jamil Poverty Action Lab. It's the center that was created by Esther Duflo and Banerjee in different universities around the world, and they run those RCTs in different fields. So this RCT I'm going to present now, that was published in the Quarterly Journal of Economics, was run in Egypt by GPAL, and it was examining the impact of an export support program. So the idea here is that, or the main research question is that small and medium firms in general, they are very they face a lot of impediments, and that's why they are underrepresented in the trade market. In other words, the number of exporting SMEs is very small. That's why to see whether this program to support SMEs could work or not, the researchers conducted a randomized evaluation in Fowa. Fowa, it's a small village in Upper Egypt, and it has a population of 65,000 individuals. It's a carpet cluster, and we have a lot of small textile firms that operate in this village. And they wanted to evaluate for SMEs with fewer than 5 employees, so micro firms, how would they benefit from an export support program. So to reach these SMEs, the researchers partnered with a certain institution in order to find the producers and foster trade relationships between those small producers and high-income OECD markets. And that's why they surveyed 219 SMEs on their production techniques, what they use, what they produce, the characteristics of the owner, the characteristics of the household, some characteristics at the household level. And they identified also all the eligible households, and then over the 219 SMEs, they selected 1/3, so around 70 SMEs to be part of the treatment. So they will benefit from the support program. And aid to artisan institution, they offered these SMEs the opportunity to produce orders for delivery to the US, which means that they know that when they will produce these products, they are going to be exported to the US. And 145 remaining SMEs, they serve as the control group, and they were not offered the same access to export opportunities. Okay? So the main findings of the paper, they tried to examine the effect of this intervention on different outcomes in order to see what is the impact of exporting on profits, on productivity, on the upgrading, and so on. And what they found based on this RCT is that profits, they have increased, and then among the potential explanations is that the rugs that was sold by these SMEs, and because they know that they will export them, so they were of a better quality. Okay. And the increase in profits also was associated to an increase in quality, and that's why it was more expensive. Okay. And that's why this increase in quality suggests that those firms, they benefited from what we call a learning by exporting, in the sense that the more they export, the more they learn, and they improve the quality of what they produce. Okay. So those are the main findings of this paper. To recap, so all those RCTs, even though they can solve the problem of randomization, because I remind you that the treatment is randomly assigned, their problem is that they require a lot of time, because we have first to get the permits, the security clearance, then start the data collection, then make sure that the treatment group is not contaminated, then measure the effect of the treatment after a year or so. So all this is time consuming. It requires a lot of money and a lot of time just to prepare it. And given that in several cases we don't have the resources, neither in terms of time nor in terms of money, to run RCTs, the option would be the quasi experiments. Because if I don't have the budget to collect new data, then in this case, I can simply run a quasi experiments. And the quasi experiment is simply what we do in general and what we're going to see in this training. Okay, so for the quasi experiments, in this case, again, we are interested in the same research question, which is we want to identify the causal impact of a program or a policy, in the sense that we don't have experimental data, so we're not going to collect new data, but we want to see whether using a data that we have, a certain intervention has an effect or not. So as long as I'm not running a new experiment through a survey and I'm collecting data, we call this a quasi-experiment. So to estimate a causal effect in a quasi-experiment framework, we need some identifying assumption that will help me identify the cause and the effect. Okay? So non-experimental methods in general, they can be classified into two types depending on the identification assumption that we're going to use. Type 1, what we call the conditional exogeneity of placement. Okay? Or we call it also the conditional exogeneity of placement to change in outcomes. In other words, it's the conditional exogeneity that will affect the outcome. Type 2 is different because I'm not interested in the outcome, but I'm interested in the instrument itself. Okay? That's why type 2, which is IV, the instrumental variables or discontinuities that can explain placement, that can explain the fact that placement can be found. Okay? So in other words, I'm interested whether the placement, how the placement can lead to a change in the outcome. And in the other, I'm looking at the instruments that lead to the placement. Okay? We're going to focus in this workshop on the first type because the conditional exogeneity of placement or the conditional exogeneity of placement to changes in outcome can be measured either using the PSM or the difference in difference or the panel. Okay? So that's what I was just saying. The type 2 non-experimental methods that we'll not cover are IV and what we call the RDD, which is the regression discontinuity design. Okay? I'm going to go quickly through in almost 5 minutes each type of or each method, just to have a brief idea about the method itself, and then in the rest of the training workshop we're going to see each method with more details at the theoretical level, at the empirical level, and at the technical level. So as I said, for type 1 that we're interested in, we're going to make the following assumption. And this point is really important because it will help us understand the rest of the tools that will be presented. So the main assumption is that we have a conditional exogeneity of placement in the sense that placement depends on some exogenous observable characteristics and not on unobservables. Okay? In other words, in this case, I assume that the selection is based on observables. Example, I'm interested in examining the effect of being a part of a global value chain, okay, on productivity. What does global value chain means? It means that a firm is exporting and importing at the same time, and it's part of a value chain at the world level. And I want to see whether being a part of a global value chain leads to higher productivity or not. Okay? In this case, the treatment is being a part of a global value chain. The problem is that I don't have money to run an RCT, so I decide to use a non-experimental or a quasi-experiment method. And in this case, I will determine two groups again, the treatment and the control group. But the treatment and the control group in this case will be determined based on observables, in the sense that I will determine the characteristics of those who participate compared to those who participate based on the same characteristics for both. So those who are part of global value chains and those who are not part of global value chains will have the same characteristic, and at the same time, some of them will be selected to be part of global value chain and others will not be selected to be part of global value chains. But initially, they have very similar or almost identical characteristics. And that's why I call them, they are selected on observables, on what we observe. Okay? Or we call them also the exogeneity of placement with respect to changes in outcomes. In this case, we assume that unobservable factors affecting changes in outcome do not affect the probability of placement, because again, as I said, I'm only interested in observables, and the unobservables that determine the placement can affect initial conditions, but they do not affect the outcome over time. So they do not affect the productivity, for instance. Okay? In the example I was just talking about. So to make it short, for type 1 methods, they rely first on observables on the one hand, and on the other, they assume that the exogeneity of placement takes place with respect to the changes in outcome. But on observables, they don't have any role in this case. Okay? For the type 1 methods, what we're going to see on day 4 is the difference in difference approach, because in this case I will compare outcomes of a treatment and the control group at one point in time, controlling for observables. That's what we call the first difference. Okay. The second difference, or the difference in difference, under again the same assumption, the weaker exogeneity of placement to change in outcome, I'm going to compare the difference from before and after the program for a treatment group and a control group. In other words, I will compare the treatment group before and after, and I will compare the control group before and after. And that's why it's a difference in difference, or a second difference, because I'm interested in two differences. In the difference, I'm comparing between I'm interested in the difference between before and after the program for the treated group and the control group. And that's what you will see next Tuesday. What you're going to see tomorrow is the propensity scores matching. And the idea of the propensity scores matching, again, it assumes conditional exogeneity of placement. Again, it's based on observables, not on unobservables. And in general, we proceed in two stages. In the first stage, we run a probit or a logit model in which the individual is selected or not. And in the second stage, I examine the effect of being selected on a certain outcome. That's why we're going to model the propensity scores matching in two stages. In the first part, it will model the selection process with a probit or a logit, and we know that they are almost the same. The only difference is what's the distribution that we assume, either a normal distribution for the probit or a logistic distribution for the logit. And here, we're going to predict the probability of participation based on observables. In other words, I will determine a treated group and a control group based on observables. So I will define this treated group relative to the control group based on the same characteristics that both of them have. Okay, and that's why, as if I'm matching each individual that participated, with an individual that did not participate, and two of them, they will be matched based on their characteristics. Okay, and in this case, I can estimate the impact of the program by looking at the mean difference, between the matched treated and control groups. Okay, so for the difference in difference, where I'm comparing before and after the treatment for both the treated and the control group on the one hand, or the PSM, where based on a certain score, I identify or I match individuals that benefited relative to those who did not benefit, and I see how the outcome variable has changed. Okay, in both cases, I assume the exogeneity of placement. Okay, and that the selection takes place based on observables. The next week, we're going to see also the random and fixed effects. And I think you might also be familiar with it, but we're going to see it from a theoretical perspective and from an empirical one, because the idea of the fixed effects is that given that we're we're concerned about unobservables, and that they could be related to a certain some certain observable characteristics. Panel data, they assume that in general we're going to control for different fixed effects or time invariant variables, which means that the remainder of the selection will be observable. And so the idea here of panel data is that given that I'm observing the same individuals over time, so I can control for their unobservables. And the rest of the selection is fully observable. Why? Because I'm following the same individual. I will be following, for instance, Tahani over time. And if I control for unobservables of Tahani over time, this will reduce the selection bias, which means that the remainder of the selection will be fully observed. Okay? And I will not go now into the details of random fixed effects and random effects because we're going to see this later. But in all cases, given that we're concerned about unobservables, that are related to something that is observable, but that I can control over time. So those three methods, which are the PSM, the difference in difference, and the panel, they all of them, they are of type 1 methods that assume that we have a conditional exogeneity of the placement, of being placed in a certain program. I'm not interested in the instrument that leads to the placement. Okay? Type 2, here it's different because we have two methods, which are the IV and the RDD. So for the IV, here there exists at least one variable that affects participation, which is the placement into a certain program, but does not affect the outcome. And we know that this is one of the most important conditions for instruments. They have to explain the first stage, but not explain the second stage. So explaining being selected into the treatment, but do not explain the outcome variable. Okay? And that's why we can call it the exclusion variable, the selection variable. I mean, it's the most important thing is that this IV has to validate or to verify this assumption on the one hand, and on the other, the IV itself has to be exogenous. And we call it that's why we call it the instrumental variable. In other words, we choose a variable that explains the fact of being part of the program, but does not explain the outcome. So it can explain in the example I was talking about, it can explain being part of a global value chain, but does not explain productivity. Clearly, it's not a simple task, but that's the assumption that we have to have in order to verify. The second approach is the RDD, which relies on a similar assumption in the sense that in this case the instrument is a certain cutoff, and we're going to see an example for that. And this cutoff determines the eligibility to participate in a certain program or not. For instance, individuals that have an income below a certain level. In this case, there is a cutoff that determines whether the individual can participate in the program or not. And the regression discontinuity design is going to focus on the differences in outcomes around the cutoff. And I'm going to explain this in a few seconds through an example. So to summarize, before we see the final example, we have seen two types of methods. Those that assume type 1 that assume the conditional exogeneity on placement, where we have three methods, the PSM, the difference in difference, and the panel. And the type 2 that assumes that the placement is done through the instrument itself, and that this includes the IV method or the RDT. Okay? Any questions before I present the last example? Anything that's not clear? Okay. So for the final example, it was a study that was done by IFPRI in 2018 to determine the impact of takaful and karam. And again, it was a social safety program whose objective was to support elderly and vulnerable people in general, to make it short. And clearly, one of the tools that could have been used in order to examine this, it could have been takaful and karama. And takaful and sorry, it could have been an RCT, a randomized control trial. And the randomized control trial again means that all individuals will be randomly assigned in the beginning, and then some of them will be selected, others will not be selected. We will give the takaful and karama program to the treated group, and not to the control group. And then the difference between the two groups will be entirely due to the impact of this program. Or perhaps compare before starting the program itself, we could have run the impact, we could have identified the individual that will benefit and those who will not benefit, but it's important to have the same individuals before and after. But the problem that took place by this time is that when the government decided to evaluate the impact of takaful and karama has already started, which means that if it already started, then I'm not able really to examine what we called those counterfactuals, so those individuals that benefited from the program, but I wanted to see their status if they did not benefit from the program, and this is unobservable. That's why the idea was to use another method. And among the other methods was, for instance, the matching, in the sense that we're going to match the individuals who benefited with those who did not benefit. And the matching techniques that you are going to see tomorrow will help us have two groups of individuals, one that benefit and the other that do not benefit. And the difference between them will be due also to the program. Okay? But the problem is that the PSM and the difference in difference, again, I remind that they are based on observables, not unobservables. And there is a concern also regarding unobservables. Why? Because unobservable differences, if unobservable differences matter, then in this case, we have to take into consideration the fact that those who did not benefit from the program based on unobservables matter. How is that? In general, those who, let's assume that the government announced the program, okay? And some of the households, they registered for the program and others did not register for the program, okay? And clearly, those who register compared to those who do not register, they have a lot of differences at both the unobservables and the observables. For instance, if we have even two women with identical characteristics, I mean, two of them they can read and write. Both of them they are living in Alexandria, for instance, and both of them they have more or less the same level of education. So on paper they are the same. We don't observe any differences. But one of them took the initiative to go to the Bureau of Registration, registered, filed her case, and so she did a more significant effort compared to another woman that on paper has the same characteristic but did not have the same will to do the whole effort. Okay? So that's why there are some unobservables. Perhaps the IQ of the first woman is higher. Perhaps she's more eager to get the money. Perhaps she's more organized, etc. Okay? So which means that in this case, I cannot really compare those who registered to the program compared to those who did not register to the program, which means that I will have to limit my analysis only to those who registered for the program. And having decided to concentrate on those who registered for the program, we observed that, or they observed that, there are a lot of variation among those who registered. So that's why they used a method called the proxy mean test score to determine the closest individual together, in the sense that this PMT, this proxy mean score, was the main factor to determine if a household is in the program or not. Okay? So if I use this proxy mean test to determine those who are in the program compared to those who are not in the program, this implies that it's not feasible to find a set of non-beneficiary household that registered for the program and at the same time that are similar to those who benefited from the program. Again, so if I use this proxy mean test, it's not feasible to find a set of non-beneficiaries, okay, who registered for the program and that are similar to those who benefited from the program. This is why the RDD, the regression discontinuity design, must be used. And given that it was hard to find non-beneficiary registrants household that are similar to all beneficiary households, what we can compare is households just below and just above the cutoff score to benefit or not. Okay? So why is this? Perhaps I will show you a graph. So here, as you can see, we have the threshold to participate. So we can determine, we have a certain outcome variable that, so we're explaining, we're examining the effect of the intervention of the Takaful and Karama program on the outcome variable. And the outcome of the program will be, as you can see, the difference between the two lines around this cutoff. Okay? So the strategy in general is very effective at determining the true impact of the program by making everything else constant, in the sense that we are really isolating the other factors. But the only problem of that is that the effect is observed around the cutoff. So in other words, we cannot really. So here I'm examining the program impact around the cutoff, not far from the cutoff. And that's why that's the main drawback. Its main advantage is that it helps us determine the effect of the program, even if it already took place, which is not the case in the RCT. For instance, in the RCT, I have the individual before and after, and all of them in the beginning, they are eligible. Here, the program already took place. I cannot compare relative to the individuals before the program. So that's why I will compare around the cutoff those who benefited compared to those who did not benefit. Okay. So again, this around this eligibility threshold and the proxy mean score determines the eligibility of households. Sorry. And in this case, even if it's hard to find non-registrants, sorry, non-beneficiary registrants household that are similar to beneficiary and registered households, I will compare households below and above the cutoff score, and this will determine the impact of the program. So the impact evaluation of Takaful and Karama was conducted using a regression discontinuity method, and the program was targeted by selecting household who fell below the threshold level based on the proxy mean test. Okay. And the RDD in this case will compare outcomes for beneficiaries below each threshold of eligibility that we have seen in this graph, right, to the outcomes of non-beneficiaries above the threshold. And that's the effect of the program. So in this case, it was feasible because we had a large number of households with a proxy mean score, with a proxy mean score near the eligibility threshold, right? And in this case, it was possible to determine the effect of the program only for those who are around this threshold. The survey took place in 2017, and it collected information on outcomes related to household expenditure and poverty, well-being, child morbidity, child health in general, healthcare utilization, women's decision-making, and the idea was to examine the effect of Takaful and Karama on a series of variables, because in theory, this Takaful and Karama program is conditional on the fact that the women will be keen to take her, sorry, not keen, will be obliged to take her children to the health centers and to the school. In other words, it's a human capital conditionality in the sense that it's conditioned on health and education. But in reality, the conditionality was not implemented because of different difficulties, and all of the women, they got the money regardless of this conditionality. Okay. So the sample for evaluation includes around 6,000 households in order to determine the effect of the Takaful and Karama program on different outcomes. And I found basically that they did not have an impact on women empowerment, and that the effect also on the conditionality did not really improve. So that's today the general overview of the different methods that we have seen. In 2 minutes, I will quickly recap everything that we have seen before we wrap up today's session. So I remind you that we started with the basic idea of identification, the problem of cause and effect, difference between correlation and causation, how the violation of the assumption of orthogonality can be very delicate because it will lead to unbiased estimators, and that it's important to make sure that this assumption is not violated. And if it's violated, we have to find for alternatives in order to make sure that we have this cause and effect. We have two types of methods. The type one, which is conditionality, based on the exogenality based on the placement, and the second one, the instrument. For the placement, we have seen three methods that we're going to detail in this workshop, which are the PSM, the difference in difference, and the IV. Those that will be covered are the RDD, the RCT, and the IV. The RCT and the RDD, we have seen some examples. The IV, I quickly explained it, but will not really cover them in details. So that was for today. Any questions? Anything that's not clear?
Just a clarification, Chahir, please.
Yes.
So we're going to be using the same link for tomorrow?
Yes.
Okay, and concerning the readings, how will we get those?
So in general, what we do after at the end of the workshop, you get a Google link with 3 subfolders. A subfolder for the slides, another subfolder for the data and do files, and a third subfolder for all the readings.
Okay, thank you.
Other questions?
Yes, Dr. Chahir, please. You said that in this every article they have used a threshold. Now I have been reviewing the paper. They have mentioned that the ultra poor households are those with the PMT scores below 3,900. My question is, how do we determine the threshold in such exercises? Is there a structured way, or it's subjective to each researcher and given the research question they have?
Well, this really depends on the research question, because at the end of the day, it can, I mean, it can depend on the national poverty line. It can depend on a survey that has been done. So it really depends on the research question. Other questions?
Mr. Shahir?
Yes.
I have a little weird question. Will we have a certificate or something that attests that we have some skills in data visualization or data analysis or not?
No, you will get a certificate that you participated in the applied microeconometric course, not a certificate for Stata.
Great, great.
Yes.
Thank you.
Other questions? Okay, so if we don't have more questions, I thank you all for your attention and for your participation in this online session, even if it was a bit long. Tomorrow you will be, Dr. Racha will be presenting the PSM. So we start at 5 p.m. Cairo time, the same link, and I will see you next week with the panel part. Thank you so much and have a nice evening.
Thank you.
Thank you.
Thank you.
Thank you.